My name is Manoj Shankar. I've been in this industry for almost 26 years, and 18 years of which has been with 3M. And obviously, working not only in India but across geographies in the Asian countries, leading research and development teams, application engineering teams, implementing technologies. And then obviously, I had a stint with VAM Organics, which I started my career after doing my MTech in Polymers and Science and Technology from IIT Delhi for about 9 years. So most of it I'm going to talk about is on the adhesion or the adhesive, because we had so many, chats, so many speakers talking about battery systems, the chemistries, right? So I'm going to cover the material science piece of it. How do you bring them together? And that's what, my focus is going to be. As I move ahead, this is just a general statement in terms of, US presentation. I'll just move on. So the number there represents how many years 3M has spent in automotive industry. So 3M, yes, we are a global company, 123 years in existence. And why the number 100 is there is the 100 years denotes basically how many years we have been in automotive. So it reflects on on the, the adhesive we have to talk about, right? The masking tape, I'm not sure how many of you know it, was discovered by 3M, brought into the world in almost 100 years ago. So we celebrate the 100 years now. So that's a start, how we connect with the automotive industry. And the innovation has been going around almost close to 130,000 patents globally. And when I look at the presence piece of it, right, in terms of the countries where we are, although we have our headquarters in Minnesota, we're close to about, 35 countries where we have labs. More than 50 countries, we have application engineering centers. And then obviously we have about 69 countries where we have, sales. Okay, I will move on to the agenda, what I'm going to cover today. How are the battery pack designs basically evolving? So when we look at, the overall drivers, right, the way to read this slide is on the top, you can see the drivers which drive typically the electrification, right? And there are subsystems, for example, the three verticals which have been put up on the slide, right? The battery, the e-motors and the power electronics. And this is the best example where, we in 3M, we connect across, see these sub-verticals and apply our knowledge of material science, lightweighting, adhesives, insulations. So there's a lot of material and functional expertise which is required to bring these materials together. The talk mainly today would be on battery systems. So I will not be covering e-motor and the power electronics. So basically I'll be covering the battery piece of it. So when we look at the battery, one of the key elements is, obviously there are cells gets converted into modules, and then modules go into the battery pack. There's a lot of assembly and disassembly that occurs, right? So both are together. There's not just bonding alone. There's a debonding also, and I'll explain you why that's required. So before, I move into the adhesive science, let us look at the evolution of battery pack designs. So the typical form factors that are there in the battery are like pouch, prismatic, cylindrical. And each of these cell geometries have their own, pros and cons, and the auto OEMs obviously, leverage it. And then the batteries are put together into modules, and the modules obviously are put into packs. But the packaging, when it comes to packaging of the modules, there's a lot of weight that gets added. Traditionally, yes, there were a lot of metals that were used. Then I believe we moved into more engineered materials. And then now, more of plastics getting used. And when we get into plastics, obviously there are medium surface energy plastics, low surface energy plastics, and low surface energy plastics are difficult to bond. So the whole focus is, how do we do lightweighting? And why do you want to do lightweighting? Because there is a charge density. The more the weight, obviously, the relevance with respect to charge density would be less. So we want to go lightweight, and that's where the bonding solutions come in. So how does the battery pack design evolve? So there are three ways in which the battery packs have been evolving in the last decade or so globally. One is obviously to do away with the, module, which is in the bottom, cell to vehicle integration. So I'm going to go from bottom to top. So removing the modules itself, so that's the non-battery side of it. So so that way you can, straight away go into lightweighting. And then there is weight and component efficiency. Reducing weight, replacing metals with plastics, right? And those are the ones where you have different materials which are brought together and assembled together. where you need to balance lot of stresses. And that's where the solutions come in. And then obviously there is work on module reduction, how many modules you can, reduce. So before going into the bonding solutions, let me just step back and give you some fundamentals of adhesives. What we see when we bond or assemble two things together is you have adhesive at the interface, right? So that's what all we see. But what we don't see is the internal strength of the adhesive that goes into it, because the internal strength is very critical. Remember, I talked about stress balance when we bring in two materials together. And that's where, the adhesive's ability to hold itself under stress, that's become critical. So when we look at fundamentals of adhesive, adhesion and cohesion, it needs to be perfectly balanced to attain the assembly requirements. And obviously, when we talk about adhesion, there are surfaces involved, surface energies and adhesive chemistries and so forth. This slide represents close to about 20,000 products. The division I represent from 3M is called as Adhesive and Tapes Division. 20,000 products, you can't put it on a single slide. Out of 60,000 products of 3M, 20,000 products are listed here as portfolios. So the best way to put it on a slide is in terms of portfolios, and we call it internally and externally as bonding continuum. Right from below thin bonding tapes, to dwell locks, to foam tapes, to structural adhesives. Right back in our engineering colleges, we less often teach students about, replacing rivets, bolts, because even now, the way we design things are with the traditional way of bolting or welding and fastening. Structural adhesives can potentially replace most of these welds. I will start with the thin bonding tapes. So thin bonding tapes, we have close to about 2,500 products in different form factors, different chemistries. Where do they go in a battery, overall system? Any cell-to-cell bonding where you need frame bonding and you need non-structural strength, right? That's where it goes. There could be insulation inserts. There could be even a lot of sensor attachments, right? So we have adhesives, tapes, which obviously does not require any thermal intervention, no other, cure mechanism. These are cured material. You just apply pressure, and these can also be automated, converted into different, parts as well. We have converter partners who take, tapes from us and can convert it. And these tapes can potentially also go for bonding many barrier materials. For example, many of the silicon foams and the other type of foam chemistries that are there in cells, that can be, these tapes can be leveraged. This slide basically gives you a glimpse in terms of the go-to adhesive families what we have in thin bonding of 3M. We have about 35 adhesive families within thin bonding, so it's very difficult to, talk about each. So these are some of the go-to relevant products which are there. So if you have to basically bond a low surface energy, there is a LSC adhesive. And if you have to have medium or a, high surface energy, there's a 200 MP adhesive. So these are all adhesive families which we have. And these are some of the applications where the thin bonding tapes can go in. Next, I will change gears and go to the middle part of the bonding continuum, which is about semi-structural strength. Because as we go less and less and bit, the most important thing is the structural integrity of the material. That's where we have VHBs, and we also have invented a very different type of technology which I'm going to showcase in the video, because it is very difficult to explain first. So you can go to the video and then I will explain you the product. So you can see the adhesive is in a spool format, it's in a rope format. Looks like a tape, but it is a semi-structural adhesive. Can give you lot of design flexibility. If you are cutting across plastics that you want to have different thicknesses, it can be done. And it is fully automated. And last but not the least, it has a stress release mechanism. It is reworkable. And there is a lot of work this is being done for reworkability. And reworkability is evolving, not from a sustainability perspective. Yes, from a sustainability perspective it is required, but also from an overhauling or a repair perspective it is evolving. So the product, as you saw in the video, basically is a spool. It's basically a rope which bonds and seals, and it is a two-core technology. It has got a pressure sensitive adhesive on the outside and it has got adhesive in the inside, and it can melt it and apply it. And it meets many of the special, UL certification which is required specifically in this space. And the most potential application is, sealing the bigger battery packs and lids, where you can basically bond it and you can actually on demand, open it. We also have a technology based in silicon where this technology can be used for sealing battery packs. This is more of a silicon technology where we have a two-part silicon which can again be used for a battery enclosure sealing application. The chemistry here is silicon. It is a 1:1, ratio adhesive. And this can also be automated, but it will require a separate automation partner for you to automate it. Now I come to the topmost piece of it, which we call as structural adhesives. So structural adhesive, when we look at, mechanical fasteners, we look at bolt, these adhesives basically give more than 2,000 pounds per square inch in any of the metal, medium surface energies, and we also have structural adhesive for low surface energies. So applications of structural adhesives range from almost from the floor, the battery floor, to frame, and frame to cover. So there are different ways, because as the industry in battery is lightweighting, there are a lot of engineered materials that come into place. And the engineered material makes a lot of pressure, but we cannot do away totally with metal. So when we have metal and plastic together, there are different side panels that come into play which need to be bonded, where you need to retain the structural integrity of the metal. So you can replace plastic, but how do you give structural integrity overall to the system? That's where, the structural adhesive plays a role. Chemistry-wise, I'm not going to go in detail. It will either become too technical. I know it's already evening time for all of you, and Saturday. So acrylic, epoxies, urethanes. Each of these chemistries are, unique, and 3M has been a leader in epoxies, and obviously you build strength in urethanes and acrylics globally. Simple way, epoxies are the most tough ones. Any tough environment, any of the Boeings that we sit in has got epoxy adhesive on the wings. So it can withstand any of the high temperature, pressure, and all those, extreme conditions. Acrylics is something where, you want really quick, fast cure it can get. Urethanes, where you need flexibility. Suppose you are bonding a thinner plastic to a metal, again, you will need a urethane chemistry, and each of them obviously has then pros and cons. This slide summarizes some of the go-to products, because in structural adhesive, again, you've got about 1,000 products. So some of the go-to products which are relevant for automotive market, right? And on the left, you can see a graph where it shows typically in 15 to 20 minutes, it picks up the strength. So that's fast, because the assembly has to be fast. And these are design-ready material. So when I say design-ready, what I mean by that is, if you have to simulate, let us say, the stress and the other properties. So if you have to simulate the stress properties, you can actually run it through a material data card. So we can do a finite element analysis. So the way to do it is, if you have typically two structures which are getting bonded, those bond areas can typically be, divided into finer element and can be mathematically modeled. And that's where the design readiness of the adhesive helps, because the material data card is unique for that adhesive. So 3M provides that. So you run less number of experiments. We talked about, building the graph fast, doing it fast in terms of design. That's where the adhesive design in terms of finite element analysis will help. So 3M has got material data cards for these products, which can be input in terms of specific properties, let us say strain rate or stress rate or Poisson's ratio, where the designs can be optimized over software rather than, doing all the prototyping physically. So saves a lot of time, lot of labor. And these can again be simulated for, different, I would say, applications. Moving on, this is one example of a potential application where a structural adhesive can be used for bonding cell to pack. I've named some of the adhesives here. One is adhesive in epoxy chemistry, other in acrylic, again another in urethane. So each of them have their own, rate of cure. So depending upon the process, how fast you want to go, how much strength you want to achieve, and what is the end duration. Basically, end application matters. An electric vehicle, if you call it a bus, will have a battery pack which is very heavy in terms of structure, versus a scooter or a four-wheeler which will have a different structure altogether. So based on the end use again and the kind of environment it will face, the adhesive can be selected. So another example where the polyurethanes adhesive, 3M adhesives can be used, epoxy adhesives can be used, and these are non-sag adhesives. You can see the advantages there, and it can be applied for vertical application. If there's something vertical you're trying to bond, it can be done. And obviously there are multiple open time options, because these adhesives, they are two-part systems. When they cure, obviously they cure fast. Okay, that brings me to almost the end of my presentation. But before I do that, I just wanted to emphasize that the journey of a battery module assembly or a battery stack overall is long. It starts from design and set, post-implementation. Till post-implementation, we are there. So the journey for each of these is unique. So it starts from design, validation. So we are there everywhere. From design, we can give you finite element analysis for a specific property of the adhesive along with your material. We can validate it as per, test protocols. We have, again, automation partners with whom we can, have integrations done to automate. I talked about the converter, so I'm skipping it. This is the material data card which I talked about. Sorry, I skipped one. So this is critical. So this is the future, because we cannot spend time in labs doing prototypes for 3 months, 10 months, 12 months. So if we can run those simulations, we can run those fatigue experiments using the material data card, it makes it very easy. And it value engineers typically, in terms of saving of doing an R&D fast. And most of these, data cards are compatible with the softwares which are available, like Abacus, Dyna, and the NSS Workbench. And we also have, I talked about automation, right? We have a dedicated bonding process center lab. We also have an R&D lab in Bangalore where we have some of the automation. But at the same time, we have a full automation facility in our St. Paul headquarters and Germany as well as in Shanghai. So we are all connected as one lab. So anytime partners, customers can walk into the lab and understand in terms of the guidance, because one is design guidance, second is how to scale it up, right?